Just as flowing water in a river constitutes a water current, moving charged particles constitute an electric current. During lightning, charges flow from the clouds to the earth. This flow of charges is not steady but momentary. Charges accumulate on the metal body of a car while it is moving. When you touch this car with bare feet, you experience a mild shock. This is because these charges get short-circuited through your body and reach the earth. These are examples of a very short duration or momentary electric current. In most of the devices that we use, there is a steady flow of charge. For example, in the working of an electric torch, a steady current passes through the circuit of the torch to make it glow. Let us conduct a simple virtual activity to understand the concept of electric current. In a closed space, a large number of positive and negative particles move around randomly. Divide the space into two parts using a vertical plane surface through which the charges cannot cross over. Cut a rectangular-shaped window in the vertical surface. Now, the charged particles can move from the left side of the partitioned space to the right side and vice versa through the window opening in the vertical plane surface. Let us now formulate a sign convention for the motion of the charged particles. The left-to-right motion of any charged particle is taken as the forward direction of motion, which is taken as positive. The right-to-left motion of any charged particle is taken as the backward direction of motion, which is taken as negative. In time t, which is equal to 10 seconds, let us assume that the number of positive charged particles crossing over from left to right is equal to A, which is equal to plus 100. The number of positive charged particles crossing over from right to left is equal to B, which is equal to minus 20. The net positive charge movement is equal to A plus B is equal to C, which is equal to plus 80. The number of negative charged particles crossing over from left to right is equal to D, which is equal to plus 40. The number of negative charged particles crossing over from right to left is equal to E, which is equal to minus 10. The net negative charge movement is equal to D plus E is equal to F, which is equal to plus 30. The net charge movement Q is equal to C minus F, which is equal to 50. A steady electric current I is denoted by Q by T. By substituting the values of Q and T, we get the value of I as 5 units. A steady current is positive when it moves in the forward direction, that is, from left to right, and negative when it moves in the backward direction, that is, from right to left. Instantaneous current at any time t is expressed as IT is equal to limit t tending to 0 delta Q by delta t, where IT is the current at time t. Delta Q is the net charge flowing across a cross-section during the time interval delta t. that is, between time t and t plus delta t. The SI unit of current is ampere and is represented by A. In the virtual activity that we just went through, we observed a random motion of the charged particles within an enclosed space. During the random motion, the charged particles not only collide with each other, but also with the wall of the enclosed space. After collision, they get deflected and move again randomly with the same velocity with which they collide. When an electric field is applied to the enclosed space, the random motion of the charged particles is changed to unidirectional flow that constitutes an electric current. This experiment can be conducted in the ionosphere layer of the atmosphere, where there are charged particles moving randomly. If an electric field is applied to a small space in this layer, the same motion of the charged particles can be observed. What are these moving charged particles that constitute an electric current? In individual atoms and molecules, the negatively charged electrons and positively charged nuclei are bound to each other and therefore are not free to move independently. Bulk matter is made up of a very large number of atoms and molecules, which are so closely packed that the electrons are no longer attached to individual nuclei. There are some materials whose electrons are totally bound to their nuclei and can't be separated even on applying an electric field. These materials are called non-conductors or insulators. In metals, some electrons are practically free to move within the bulk material. These electrons are called free electrons. When an electric field is applied across metallic objects, an electric current develops in them due to the unidirectional flow of these free electrons. Therefore, metals are called conductors. Electrolytic solutions are also categorized as conductors, as both positive and negative charges move when an electric field is applied. In this chapter, we will emphasize on solid metal conductors, where a current is constituted by the movement of negatively charged free electrons in the background of fixed positive ions. Consider a metal object when no electric field is present. Electrons in the object will be moving randomly and colliding with the fixed ions. An electron, after colliding with an ion, gets deflected with the same velocity with which it collides. The direction of velocity of the electron after collision is completely random. There is no preferential direction for the velocities of the electrons. On average, the number of electrons traveling in any particular direction will be equal to the number of electrons traveling in the opposite direction. Therefore, there is no net electric current. Let's apply an electric field to the metal and see what happens to the motion of these electrons. To observe the motion of electrons very clearly, let us use a conductor in the shape of a cylinder of radius r. We take two thin circular discs made of a dielectric material of the same radius r as that of the cylinder. There are q number of positive charges distributed across one of the discs and q number of negative charges distributed across the other disc. These two discs are attached to the two flat surfaces of the cylinder, creating an electric field which is directed from the positively charged disc to the negatively charged disc. The electrons are accelerated and move towards the positive charge. On reaching the positive charge, they neutralize the charges on the disc. The unidirectional motion of these electrons constitutes an electric current. This electric current exists only for a very short time, that is, till the charges are neutralized. We can attach the two ends of a battery or a cell to the two discs to maintain a steady electric field and thereby obtain a steady current. Ohm's law states that V is proportional to I, where V is the potential difference across the conductor and I is the current flowing through the conductor. Let this be equation 1. To replace the proportionality sign by equality, we introduce a constant and write equation 1 as V is equal to Ri, where R is the constant of proportionality and is called the electrical resistance of the conductor. Let this be equation 2. The SI unit of resistance is ohm. The resistance R of a conductor depends on the composition of the conducting material and the dimensions of the conductor. To understand how the dimensions of a conductor affect its resistance, let us conduct two simple activities. Let's take two identical conductors of length L and cross-sectional area A. Place them side by side such that their ends touch each other, so that the length of the combination is 2L. The current I flowing through this combination is the same as that flowing through the individual conductors. The potential difference V across the ends of each conductor should be the same as they are identical and the same current I is flowing through them. The potential difference across the ends of the combination of the two conductors is 2V. The resistance of each conductor is expressed as R is equal to V by I. The resistance of the combination of conductors is represented by RC. RC can be calculated by applying the above formula for the combination. Substituting V by I is equal to R in the above equation, we get RC is equal to 2R. From this activity, we can conclude that resistance R is directly proportional to the length L of the conductor. Let this be equation 1. Coming to activity 2. Let us divide the conductor into two by cutting it lengthwise so that it can be considered as a combination of two identical conductors of length L, but each having a cross-sectional area of A by 2. The potential difference applied across the two conductors is V. If I is the current through the combination of the conductors, then the current flowing through each conductor is I by 2. Then, the resistance of each conductor is obtained as equal to 2R. From this activity, we can conclude that having the area of cross-section of a conductor doubles its resistance. Generalizing, we can write resistance R of a conductor is inversely proportional to its cross-sectional area A. Let this be equation 2. Combining equations 1 and 2, we can write resistance R is proportional to L by A. Let this be equation 3. Replacing the proportionality sign with equality, we can write equation 3 as R is equal to rho into L by A. Let this be equation 4, where rho is the constant of proportionality, which depends on the material of the conductor and is called resistivity. Substituting equation 4 in Ohm's law, we get V is equal to I into rho into L by A. Let this be equation 5. Current per unit area is called current density, J. Current density J is expressed as I by A, where area A is normal to the direction of the current I passing through the conductor. Let this be equation 6. The SI unit of current density, J, is ampere per meter square. When E is the magnitude of the uniform electric field in the conductor of length L, then the potential difference V across the conductor is expressed as V is equal to EL. Let this be equation 7. Substituting equations 6 and 7 in 5, we have EL is equal to the product of J, rho and L. On simplifying the above equation, we get E is equal to J into rho. Let this be equation 8. The above equation can be written as J is equal to E into 1 by rho. Substituting 1 by rho is equal to sigma in the above equation, we get J is equal to E into sigma, where sigma is the conductivity of the conductor. This equation is the equivalent form of Ohm's law. An electrolytic cell is a device which maintains a steady electric current in an electric circuit. Let us now understand the construction and working of an electrolytic cell. An electrolytic cell consists of two electrodes, positive P and negative N, immersed in an electrolytic solution, also called an electrolyte. The electrodes, when dipped in the electrolyte, exchange charges with the electrolyte. Due to the exchange of charges, the positive electrode P acquires a potential difference Vp between itself and the electrolyte solution immediately adjacent to it. The magnitude of Vp is always greater than 0. Due to the exchange of charges, the negative electrode N acquires a negative potential Vn relative to the electrolyte adjacent to it. The magnitude of Vn is equal to or greater than 0. When there is no current, the potential throughout the electrolyte is the same. Let us now understand the concept of the electromotive force of an electrolytic cell. The potential difference V between P and N is Vp minus of minus Vn, which is equal to Vp plus Vn. Let this be equation 1. The voltage or electric potential difference across the terminals of a cell when no current is drawn from it is its EMF. Thus, E is equal to Vp plus Vn, which is greater than 0. Let this be equation 2. EMF is the short form of electromotive force. E actually represents potential difference, but was called electromotive force by the scientist who first used it, and the name continues to date. So far, we have studied the components in a cell and how potential difference comes into existence. Let us now connect the two electrodes of the cell to the two ends of a resistor to understand how a cell actually functions when it is connected in a circuit. A resistor with a resistance equal to R is connected across the cell. A current I is established from C to D. As a steady current is maintained, the same current I passes from P to N in the external circuit and from N to P within the electrolyte present inside the cell. As the current passes through the electrolyte, it must have a finite resistance R, which is known as the internal resistance of the cell. To clearly understand the difference between potential difference and EMF, let us replace the resistor R in the circuit with a resistor of infinite resistance. We can now write I is equal to V divided by R equal to 0. Here, V is the potential difference between P and N measured across the resistor. From equations 1 and 2, V, the potential difference between P and N measured across the electrolyte, is written as V is equal to E. Let this be equation 3. From equation 3, we can conclude that EMF, E, is the potential difference between the positive and negative electrodes in an open circuit. That is, when there is no current passing through the cell. Let us now return to the original circuit consisting of a resistor with a finite resistance. Let us now connect the two electrodes of the cell to the two ends of a resistor to understand how a cell actually functions when it is connected in a circuit. A resistor with a resistance equal to R is connected across the cell. A current I is established from C to D. As a steady current is maintained, the same current I passes from P to N in the external circuit and from N to P within the electrolyte present inside the cell. As the current passes through the electrolyte, it must have a finite resistance R, which is known as the internal resistance of the cell. To clearly understand the difference between potential difference and EMF, let us replace the resistor R in the circuit with a resistor of infinite resistance. We can now write I is equal to V divided by R equal to 0. Here, V is the potential difference between P and N measured across the resistor. From equations 1 and 2, V, the potential difference between P and N measured across the electrolyte, is written as V is equal to E. Let this be equation 3. From equation 3, we can conclude that EMF, E, is the potential difference between the positive and negative electrodes in an open circuit. That is, when there is no current passing through the cell. Let us now return to the original circuit consisting of a resistor with a finite resistance. Now, as the resistance is finite, I is not equal to 0. As I is not equal to 0, I also has to pass through the electrolyte to maintain a continuous flow of charge. The electrolyte has a finite resistance R, called the internal resistance of the cell. According to convention, the current from P to N through the circuit is positive. As the current I in the electrolyte is from N to P, the current through the electrolyte is taken as negative. In this case, the potential difference V between P and N is denoted by V is equal to Vp plus Vn minus I into R. Substituting from equation 2, we can write V is equal to E minus I into R. Let this be equation 4. Applying Ohm's law to the external circuit, we have V is equal to I into R, where V is the potential difference across R. Let this be equation 5. Combining equations 4 and 5, we get I into R is equal to E minus I into R. On rearranging the terms in this equation and simplifying, we get I is equal to E divided by R plus R. The maximum current that the cell can provide is when R is equal to 0. Then we have I maximum is equal to E divided by R. To avoid permanent damage to the cell, the maximum current allowed is far less than the value calculated using this formula. Let's take a conductor AB in which a current I is flowing from A to B. The electric potential at point A is VA and at B it is VB. As the current is flowing from A to B, the voltage at A is greater than the voltage at B. The potential difference V between points A and B is expressed as V is equal to VA minus VB. Let this be equation 1. As V of A is always greater than V of B, V will always be greater than 0. Let the amount of charge flowing from point A to B be delta Q in the time interval delta T. Delta Q can be expressed as the product of I delta T. Let this be equation 2. The potential energy of the charge at the initial point A is delta QVA. The potential energy of the charge at point B is delta QVB. A change in potential energy between points A and B is expressed as delta U potential, which is equal to final potential energy minus initial potential energy, which is equal to delta Q into VB minus VA. From equation 1, we know that V is equal to VA minus VB. Therefore, VB minus VA is equal to minus V. Let this be equation 3. From equations 2 and 3, delta U potential is equal to minus I delta TV. Let this be equation 4. Since the value of delta U potential is negative, it is less than 0. The law of conservation of total energy states that the total amount of energy in an isolated system remains constant over a period of time. Applying the law of conservation of total energy between points A and B, since the potential energy of the charge is decreasing, its kinetic energy must increase. Therefore, an increase in kinetic energy K of the charges is expressed as delta K is equal to minus delta U potential. From equation 4, we can say that delta K is equal to minus I delta TV. This implies that delta K is equal to I delta TV. Let this be equation 5. Since the value of delta K is positive, its value is greater than 0. If the charges move freely through the conductor, their kinetic energy should increase, and they should move with greater velocity. But we know that on an average, these charge carriers do not move with acceleration, but with a steady drift velocity. This is because the free electrons collide with the ions while in transit. Due to these collisions, the kinetic energy gained by the charges is transferred to the heavy ions. And these ions vibrate more vigorously, thereby heating up the conductor. The heat dissipated by the vibrating ions is represented by delta W. This delta W is nothing but the increase in the kinetic energy of the charged particles. Therefore, delta W is equal to delta K. From equation 5, we can say that the amount of energy dissipated is expressed as delta W is equal to I delta TV. Let this be equation 6. The energy dissipated per unit time is termed as the power dissipated and is represented by P. Therefore, we can write P is equal to delta W by delta T. Substituting the value of delta W from equation 6 in the above equation, we get P is equal to I delta TV by delta T. On further simplifying, we get P is equal to IV. Let this be equation 7. According to Ohm's law, we have V is equal to IR. On substituting the value of V from Ohm's law in equation 7, we get P is equal to I square R. Let this be equation 8. Ohm's law can be rewritten as I is equal to V by R. Substituting the value of I in equation 8, we get P is equal to V by R whole square into R. This implies that P is equal to V square by R. Let this be equation 9. P, which represents the power dissipated or lost, is also called ohmic loss in a conductor of resistance R carrying a current I. This dissipated power P is utilized to heat the filament of an electric bulb to incandescence and radiate heat and light energy. Power is supplied to this resistor by an external source such as an electric cell. Similarly, there is power loss when a current I is transmitted from the point of generation to the point of utilization through transmission cables. The distance between these 2 points is often very large. the transmission cables have a certain resistance due to which there is a huge power loss. Using equation 8, that is, P is equal to I square R, we can derive an expression to calculate the power loss due to resistance in the cables. Power loss in the cable PC is due to its resistance RC, which is expressed as PC is equal to I square RC. Let this be equation 10, where I is the current flowing through a cable. According to equation 7, P is equal to IV, where P is the power generated at source, V is the voltage generated, and I is the current flowing through the cable. Rearranging equation 7, we get I is equal to P by V. Let this be equation 11. Substituting equation 11 in 10, we get PC is equal to P by V whole square into RC. That is, PC is equal to P square by V square into RC. Let this be equation 12. This equation helps calculate the power loss PC due to the resistance RC in the transmission cable. In equation 12, we can say that the values of power P generated at source and the resistance RC of the cable are constants. Therefore, it implies that the power loss by the cable PC is inversely proportionate to the square of the voltage generated. Therefore, to minimize the power loss in transmission cables, the voltage of the power produced at the point of power generation is stepped up using a step-up transformer before it is transmitted. This very high voltage is converted to low voltage using a step-down transformer placed very near to the point of utilization of power. As you learnt earlier, there are various elements used in an electrical circuit, such as a resistor R, voltmeter V, ammeter A, and battery, which are represented here. These will help you understand the various circuits dealt with in this module. Resistors are one of the important components in a circuit. Resistors are joined together to form various types of combinations to obtain the required resistance in the following three ways. 1. Series combination. 2. Parallel combination. And 3. Mixed combination made up of both series as well as parallel combinations of resistors. We obtain a series combination of resistors by joining one of the two endpoints of a resistor to the next resistor. We can make a series combination using 2, 3 and so on up to n resistors. We obtain a parallel combination of resistors by joining one end of all the resistors and similarly joining the other end of all the resistors. A parallel combination can be made using any number of resistors. A mixed combination of resistors is obtained by connecting some resistors in series and some resistors in parallel combination and then connecting the two combinations. So far, we have seen how to build various types of combinations of resistors. Next, we will learn about equivalent resistance of any combination of resistors in a circuit. Equivalent resistance is the resistance of a single resistor that can replace the given combination of resistors in the circuit without affecting the total current in the combination and the voltage across the combination. Let us now derive equations to find the equivalent resistance of the various types of combinations of resistors. Equivalent resistance of a series combination is obtained as follows. AB and CD are two resistors with resistances R1 and R2 joined in series as shown in the circuit diagram. A voltage V is applied across points A and D by joining them to the two terminals of a battery. V is the potential difference between points A and D. The charge that leaves R1 enters R2. As current is the measure of the rate of flow of charge, the same current I must flow through R1 and R2. According to Ohm's law, V is equal to I into R, where V is the voltage across the resistor, I is the current flowing through the resistor, and R is the resistance of the resistor. Applying Ohm's law to resistor 1, the potential difference across R1 is denoted by the equation V1 is equal to I into R1. Let this be equation 1. The potential difference across R2 is denoted by the equation V2 is equal to I into R2. Let this be equation 2. The potential difference V across A and D, that is, the series combination, can be written as V is equal to V1 plus V2. Let this be equation 3. Substituting equations 1 and 2 in 3, we get V is equal to IR1 plus IR2. V is equal to I into R1 plus R2. Let this be equation 4. Equation 4 can be written in the form V is equal to I into R equivalent. Let this be equation 5. From equations 4 and 5, we can write R equivalent is equal to R1 plus R2. Let this be equation 6. From equation 6, we conclude that when two resistors R1 and R2 are connected in series, the combination has an equivalent resistance equal to R1 plus R2. When three resistors of resistances R1, R2 and R3 are connected in series, the equivalent resistance for this combination is equal to R1 plus R2 plus R3. We can extend this to a series combination of n number of resistors with resistances R1, R2 and so on up to Rn. The equivalent resistance of this combination is equal to R1 plus R2 and so on up to Rn. Now let us consider a parallel combination of resistors AB and CD with resistances R1 and R2 connected as shown to a battery of potential difference V. The equivalent resistance Req of this parallel combination is obtained as follows. The charge that flows from the source, that is the battery, splits and flows out partly through R1 and partly through R2. I is the rate of flow of charge from the source, that is the battery. I1 is the current through resistor R1, and I2 is the current through resistor R2. We can now write I is equal to I1 plus I2. Let this be equation 7. Applying Ohm's law across R1 and R2 individually, we can write V is equal to I1 into R1 and I1 is equal to V by R1. Let this be equation 8. Voltage V applied across the two resistors is the same as they are connected parallel to the same battery. Therefore, we can write V is equal to I2 R2 and I2 is equal to V by R2. Let this be equation 9. Substituting equations 8 and 9 in equation 7, we get I is equal to V by R1 plus V by R2 and I is equal to V into 1 by R1 plus 1 by R2. Let this be equation 10. Equation 10 can be rewritten in the form I is equal to V into 1 by Req. Let this be equation 11. Req is the equivalent resistance of the parallel combination of resistors. From equations 10 and 11, we can write 1 by Req is equal to 1 by R1 plus 1 by R2. Let this be equation 12. Using equation 12, we can calculate the equivalent resistance Req of the parallel combination of two resistors. Similarly, when there are n resistors connected in the parallel combination, we can write 1 by Req is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. Now let us consider a situation where some resistors are connected in series and some resistors are connected in parallel. The equivalent resistance of such a series and parallel combination is obtained as follows. In the circuit, three resistors of resistances R1, R2 and R3 respectively are connected in a mixed combination. R2 and R3 are in parallel combination. Their equivalent resistance R23EQ is calculated using equation 12. 1 by R23EQ is equal to 1 by R2 plus 1 by R3. Now, R1 and R23EQ form a series combination. Their equivalent resistance R123EQ is calculated using equation 6. R123EQ is equal to R23EQ plus R1. We can calculate the equivalent resistance of any combination of resistors using the basic equations 6 and 12. We use one cell in an electric circuit to understand the concept of EMF and internal resistance of a cell. We will now look at different combinations of cells and conceptualize an equivalent EMF and equivalent internal resistance for these combinations, just as we did in the case of resistors in series and in parallel combinations. Cells are connected either in series or in parallel combinations to obtain the required voltage and current in a circuit. To calculate currents and voltages in a given circuit, the combination of cells is replaced by an equivalent cell that gives the same EMF as that of the combination. First, let us consider a combination of two cells that are connected in series. One terminal of each cell is joined together, leaving the other terminals of the two cells free. There are two ways to make a series combination of two cells. In the first way, the negative electrode of the first cell is connected to the positive electrode of the second cell. In the second way, the negative electrode of the first cell is connected to the negative electrode of the second cell. Let us now analyze the first case, where the negative electrode of the first cell is connected to the positive electrode of the second cell. E1 is the EMF of cell 1. R1 is the internal resistance of cell 1. E2 is the EMF of cell 2. R2 is the internal resistance of cell 2. The potential at point A is VA. The potential at point B is VB. The potential at point C is VC. VAB is the potential difference between points A and B, which also represents the potential difference between the positive and negative terminals of the first cell. We know that terminal voltage V is equal to E minus I into R. Substituting the corresponding expressions of cell 1 in this equation, we can now write VAB is equal to E1 minus I into R1. Let this be equation 1. Similarly, for the second cell, we can write VBC is equal to VB minus VC is equal to E2 minus I into R2. Let this be equation 2. We can now write the potential difference between the terminals A and C of the combination of cells as VAC is equal to VA minus VC, which is equal to VA minus VB plus VB minus VC. Substituting from equations 1 and 2, we have VAC is equal to E1 minus I into R1 plus E2 minus I into R2. Rearranging and simplifying the right side of the equation, we have VAC is equal to E1 plus E2 minus I into R1 plus R2. Let this be equation 3. Writing equation 3 in the form V is equal to E minus I into R, we get VAC is equal to EEQ minus I into REQ, where EEQ is the equivalent EMF and REQ is the equivalent internal resistance of the combination of the cells. Let this be equation 4. Comparing equations 3 and 4, we can write EEQ is equal to E1 plus E2. Let this be equation 5. REQ is equal to R1 plus R2. Let this be equation 6. Equation 5 is used to calculate the equivalent EMF of the series combination of two cells. Equation 6 is used to calculate the equivalent internal resistance of the series combination of two cells. Let us now observe changes in the equations when the negative terminal of the first cell is connected to the negative terminal of the second cell and E1 is greater than E2. Let us call this case 2. We will now proceed with the derivation just as in case 1. As E1 is greater than E2, current I leaves the positive terminal of the first cell, goes through the external circuit and moves from the positive terminal of the second cell to its negative terminal, and finally reaches the negative terminal of the first cell. The current leaves the second cell from its negative terminal. As the direction of the current I within the second cell is opposed by its EMF E2, E2 is taken as negative in the equation for VBC. Hence, we get VBC is equal to minus E2 minus I into R2. Let this be equation 2. Writing the equation for VAC. By substituting equations 1 and 2, simplifying and putting it in the equivalent form, we get EEQ is equal to E1 minus E2. Let this be equation 5. From equations 3 and 4, we can write REQ is equal to R1 plus R2. Let this be equation 6. We can now extend these rules to any number of cells in a series combination. Rule number 1. The equivalent EMF of a series combination of n number of cells is the algebraic sum of their individual EMFs. If, in the combination, the current leaves any cell from the negative electrode, the EMF of that cell will bear a negative sign. Rule number 2. The equivalent internal resistance of a series combination of n number of cells is the sum of their internal resistances irrespective of the orientation of the terminals of the cells in the series combination. Let us now consider a parallel combination of two cells. The positive terminals of the two cells are connected to each other. Similarly, the two negative terminals are connected to each other. I1 is the current leaving the positive electrode of the first cell. Similarly, I2 is the current leaving the positive electrode of the second cell. At junction point B1, I1 and I2 flow in and flow out as I into the external circuit. At any point in a circuit, the total charge flowing in must be equal to the total charge flowing out. So, at junction point B1, we can write I is equal to I1 plus I2. Let this be equation 1. VB1 is the potential at point B1. VB2 is the potential at point B2. The potential difference between points B1 and B2 taken across cell 1 can be written as V is equal to VB1 minus VB2. V is equal to E1 minus I1 into R1. Rearranging the terms, we can write I1 is equal to E1 minus V divided by R1. Let this be equation 2. Similarly, taking points B1 and B2 to be across cell 2, we can write V is equal to VB1 minus VB2. V is equal to E2 minus I2 into R2. Rearranging the terms, we can write I2 is equal to E2 minus V divided by R2. Let this be equation 3. Substituting equations 2 and 3 in equation 1, we get I is equal to E1 minus V divided by R1 plus E2 minus V divided by R2. On simplifying and rearranging the terms, we get I is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. By further rearranging the terms, we can write V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 divided by R1 plus R2. Let this be equation 4. We can replace the combination of two cells with one cell of EMF, EEQ, and internal resistance, REQ. We can now write V is equal to EEQ minus I into REQ. Let this be equation 5. From equations 4 and 5, we can write EEQ equal to E1 R2 plus E2 R1 divided by R1 plus R2. Let this be equation 6. REQ is equal to R1 R2 divided by R1 plus R2. Let this be equation 7. Equation 7 can be written as 1 by REQ is equal to 1 by R1 plus 1 by R2. Let this be equation 8. Dividing equation 6 by equation 7 and rearranging the terms, we get EEQ divided by REQ is equal to E1 by R1 plus E2 by R2. Let this be equation 9. In the circuit that we used, two positive terminals are joined to each other, and similarly, two negative terminals are joined to each other, and currents I1 and I2 are flowing out of the positive terminals. If the negative terminal of the second cell is connected to the positive terminal of the first, equations 8 and 9 are still valid by replacing E2 with minus E2. Equations 8 and 9 can be extended when n cells of EMF E1 to En with internal resistances R1 to Rn are connected in parallel combination. They can be replaced with a single cell of EMF EEQ and internal resistance REQ. We can write 1 by REQ is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. EEQ by REQ is equal to E1 by R1 plus E2 by R2 plus and so on up to En by Rn. Most electric circuits are made up of a number of resistors and cells interconnected in a complicated way. The formulae that we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Kirchhoff's rules are used to analyze these complicated electric circuits. Rule number 1. Kirchhoff's first rule is also called Kirchhoff's point rule or Kirchhoff's junction rule or nodal rule. This rule is based on the principle of conservation of charge. At any node or junction in a circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. This rule can also be expressed as the algebraic sum of currents in a network of conductors meeting at a point or node is 0. The current entering the junction is taken as positive and the current leaving the junction is taken as negative. This statement can be expressed mathematically as sigma Ik. K ranging from 1 to n is equal to 0. Rule number 2. Kirchhoff's second rule is also known as Kirchhoff's loop or mesh rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. The electric potential at any point in a closed loop depends only on the location of the point in the loop. So, starting from any point in the loop, if we come back to the same point, the sum of potential changes must be 0. ABCDA is one of the closed loops in a complicated circuit. Starting from any point in the loop, we walk through the loop either in a clockwise or anti-clockwise direction and write down the change in potential. Let us start from point A and walk through the loop in the clockwise direction. That is, ABCDA. And note down the change in potential. AB. While moving from point A to point B, we go from the negative terminal of the battery to the positive terminal of the battery. Therefore, the change in potential is plus V, which is the voltage of the battery. BC. Current I1 is passing through R1. The direction of current I1 and the direction of walk-through is the same. The change in potential is minus I1 into R1. Here, you should clearly understand why the change in potential is minus. Charges always flow from a point at higher potential to a point at lower potential. Therefore, point B is at a higher potential compared to point C. We are calculating the potential change between points C and B, which is the potential at C minus the potential at B. Hence, the change in potential is negative. CD. Current I2 passes through R2. The direction of I2 is opposite to the direction of walk-through. Current always flows from a higher potential to a lower potential. Therefore, the change in potential is minus of minus I2 into R2, which is equal to plus I2 into R2. Another way of expressing this concept is as follows. Here, charges are flowing from D to C. Therefore, point D is at a higher potential compared to point C. As we are calculating the potential change between points D and C, which is the potential at D minus potential at C, it is positive. DA. Current I3 is passing through R3. The direction of I3 and the direction of walk-through is the same. The change in potential is minus I3 into R3. To apply Kirchhoff's rule 2, we add all these changes in potential and equate it to 0. Let us now apply Kirchhoff's rules to find the current in each branch of this complicated circuit. There are two important steps in the procedure. Step 1. We label and indicate the direction of current in each branch of the circuit. Next, apply Kirchhoff's first rule at every junction point. Step 2. We apply Kirchhoff's second rule to the closed loops in the circuit. The number of closed loops chosen depends on the number of unknown currents as per step number 1. Let us start with the branch AC for labeling the current and its direction. Current I1 leaves the positive terminal of a 10-volt battery. Therefore, the direction of current I1 is from C to A. Next, let us take the branch BED. Let us assume that the current I2 leaves the 5-volt battery from its positive terminal. Therefore, the direction of I2 is from E to B and D to E. The assumption that we have made for the direction of current I2 may be wrong. In that case, at the end of the solution of the problem, we obtain a negative value for I2. Then, we change the direction of I2 and write the answer. The three branches BA, CA and DA meet at the nodal point A. We have already labeled the current in branch AC. We have to now label the currents in the remaining two branches. Let us assume that a current I3 is flowing in branch BA in the direction A to B. We are now left with only one branch, that is, AD, to which we have to label the current. Let us assume that the current is flowing from A to D. We can now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodal point B. Three branches AB, EB and CB meet at point B. The current in branches AB and EB are already labelled. We have to find the current in branch BC. Currents I3 and I2 are flowing towards point B. Therefore, the current in branch CB must flow out of the point. We now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodal point C. There are three branches meeting at point C. Only the current in branch DC is not known. Let us assume that the current in this branch is flowing from C to D. We now apply Kirchhoff's first rule at node point C to find the magnitude of the current in branch DC. We have labelled the currents in all the branches. We have a self-check to see whether the magnitudes of the current in the branches that we calculated are correct. Let us apply Kirchhoff's first rule at nodal point D. As Kirchhoff's first rule is satisfied, the current in the branches that we have calculated is correct. There are three unknowns in the circuit. They are I1, I2 and I3. To find the values of these unknowns, we apply Kirchhoff's second rule to any three closed loops in the circuit. Loop ABCA. Let us start from the negative terminal of the 10-volt battery. Walk through the loop in a clockwise direction and add the potential changes. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 1. Loop ADCA. Let us again start from the negative terminal of the 10-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes step by step and equate it to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 2. Loop ABCDE. Let us start from the negative terminal of the 5-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes and equate it to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 3. We have so far obtained 3 simultaneous equations with 3 unknowns. On solving these 3 simultaneous equations, we get the values of the unknown currents as shown. Substituting these values, we get the current in the various branches as shown. The Wheatstone bridge is an electrical circuit shaped like a rhombus. ABCD. The 4 sides of the rhombus are made up of 4 different resistors. R1 to R4. Across the vertical diagonal BD of the rhombus, a galvanometer is connected to detect current. Across the horizontal diagonal AC, a cell is connected. I1 to I4 are the currents through the corresponding resistors R1 to R4. IG is the current passing through the galvanometer. Let G be the resistance of the galvanometer. The formulae we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Let us now apply Kirchhoff's junction rule at junction points B and D. At point B, I2 minus Ig minus I4 is equal to 0. Let this be equation 1. At point D, I1 plus Ig minus I3 is equal to 0. Let this be equation 2. Let us now apply Kirchhoff's loop rule to the 2 closed loops, ADBA and CBDC. Loop ADBA. Across points A and D, by applying the rule, we get minus I1 R1 plus IgG plus I2 R2 is equal to 0. On simplifying, we get I1 R1 is equal to I2 R2 plus IgG. Let this be equation 3. Loop CBDC. Across points B and C, by applying the rule, we get I4R4 minus IGG minus I3R3 is equal to 0. On simplifying, we get I4R4 is equal to I3R3 plus IGG. Let this be equation 4. As a special case, the values of R1 to R4 are chosen in such a way that IG becomes 0. Now, substituting IG equal to 0 in equation 1 and simplifying, we get equation 5. Substituting IG equal to 0 in equation 2 and simplifying, we get equation 6. Substituting IG equal to 0 in equation 3 and simplifying, we get equation 7. Substituting IG equal to 0 in equation 4 and simplifying, we get equation 8. Substituting for I3 and I4 from equations 5 and 6 in equation 8, we get I1 divided by I2 is equal to R4 divided by R3. Let this be equation 9. From equations 7 and 9, we can write R2 divided by R1 is equal to R4 divided by R3. Let this be equation 10. Equation 10 denotes the relationship between the 4 resistors for the galvanometer to produce zero or null deflection. This relation is therefore called the balance condition. The application of this balance condition is a practical method to determine an unknown resistance. Let us assume that R4 is the unknown resistance. R1 and R2 are known resistances. We gradually change the value of R3 till the galvanometer shows null deflection. The bridge now is in balanced condition and we can apply equation 10. Rearranging the terms in equation 10, we can write R4 is equal to R2 into R3 by R1. Let this be equation 11. Equation 11 is used in a practical circuit, which is called the meter bridge. The schematic diagram of a meter bridge is as shown. A meter bridge consists of a 1 meter long standard resistance wire of uniform cross-section held taut between two ends of a metallic strip bent at right angles at the ends, placed alongside a meter scale. There are two gaps, one on the left and the other on the right. In the horizontal part of the metallic strip were two resistors, one of which is known and the other unknown, are attached. The end points A and C, where the wire is clamped to the metallic strip, are connected to the cell. One end of the galvanometer is connected to the midpoint B of the metallic strip between the two gaps in it. The other end of the galvanometer is connected to a jockey, which is a metallic rod with one end shaped like a knife edge. The knife edge end of the jockey slides over the wire to make electrical contact. R is the unknown resistance of a given resistor which we have to determine, and the resistor is connected across the right gap in the metallic strip. A standard resistance, S, in the form of a resistance box, is connected across the left gap in the metallic strip. The knife edge end of the jockey is moved along the wire until the galvanometer shows a null reading. Let D be the position of the jockey on the wire when the null reading is obtained. Let R be the resistance per centimeter of the standard wire. As the area of cross-section of the standard wire is constant, its resistance is proportional to its length. Thus, the resistance of the AD part of the wire is equal to R into L, and the resistance of the DC part of the wire is equal to R into 100 minus L. The Wheatstone bridge and meter bridge circuits are very similar. The table shown gives the comparison of resistances between the Wheatstone bridge and the meter bridge. As the current in the galvanometer of the meter bridge is 0, the circuit in the meter bridge is a balanced one, and hence we can apply equation 11 to the circuit. Substituting the expressions for the resistances in the meter bridge in equation 11 and simplifying, we get the expression for the unknown resistance R is equal to S into 100 minus L divided by L. Thus, we find the resistance of an unknown resistor using the principle of the Wheatstone bridge in a meter bridge circuit. Consider a metal conductor. Current in a conductor is due to the valence electrons in it. The valence electrons are not bound to any particular atom and are free to move about within the volume of the conductor. These electrons are called the conduction electrons. Rest of the conductor is made of relatively heavy positive atoms that are referred to as the lattice. Let us consider a conductor that is not connected to any battery or to a cell. Hence, there isn't any electric field. The free electrons move at random, collide within themselves and with the ions in the lattice. The radius of an electron is very small as compared to that of an atom. Hence, the collisions between conduction electrons and other electrons are neglected. As the conduction electrons move at random, they have different velocities in different directions. Let the velocities of the free electrons at any given instant be u1, u2, and so on up to un for n number of electrons. As the directions of the velocities are random, the vector sum of the velocities of all the electrons is equal to 0. Hence, the average velocity of all the electrons at the instant u is equal to 0. Let this be equation 1. The motion of these free electrons is called thermal motion, as the motion of these electrons depend on their average kinetic energy. Average kinetic energy of the electrons depends on the temperature of the conductor. Since the average velocity of the conduction electrons at any instant is 0, there is no net transport of electric charge. Thus, there is no net electric current through the conductor. Now let us consider a conductor connected to a source of electromotive force, such as a cell or a battery. When the conductor is connected to an external source, an electric field is applied across the conductor. Due to the electric field, the free electrons are accelerated in the direction opposite to that of the field. The magnitude of the electric charge on an electron is E. If E is the magnitude of the applied electric field strength, the force on the electron F is equal to E into E. If m is the mass of the electron, then the acceleration of the electron A is equal to the ratio F to m, which is equal to E into E by m. Let this be equation 2. Due to the acceleration, the free electrons gain velocity and hence kinetic energy. With the acquired kinetic energy, the free electrons collide with the atoms within the conductor. During such collisions, the electrons give up their energy to the atoms. Hence, their velocity decreases. Immediately after the collision, the free electrons are accelerated due to the applied electric field. This acceleration gain increases the velocity and thus the kinetic energy of the electrons. The electrons again collide and lose their kinetic energy. Due to these repeated collisions, the average acceleration of the electrons is reduced to 0. Hence, the average velocity of the free electrons is constant and is directed opposite to the direction of the applied electric field. The average velocity gained by the free electrons in a conductor when subjected to an electric field is called the drift velocity. Let us find an expression for the drift velocity of the conduction electrons in a conductor when subjected to an electric field. Earlier, we considered the velocities of n number of conduction electrons at any given instant to be u1, u2, so on till un. Now, when the electrons are subjected to the electric field, let their velocities be v1, v2, so on till vn. Here, v1 is equal to u1 plus a into tau 1, where tau 1 is the time between two successive collisions of the first electron. Similarly, v2 is equal to u2 plus a into tau 2, where tau 2 is the time between two successive collisions of the second electron. So on till Vn is equal to Un plus a into tau n. The average velocity of all the free electrons is equal to the drift velocity Vd. Hence, Vd is equal to V1 plus V2 plus so on plus Vn divided by n. Substituting the expressions for V1, V2, so on till Vn in the expression for Vd and simplifying, we get Vd is equal to U plus a into tau. This average time elapsed between two successive collisions of a conduction electron is called the relaxation time. It is of the order of 10 power minus 14 second. This implies that an electron is free from any collision for the duration of 10 power minus 14 second and is relaxed. The mean distance travelled by the electron during the relaxation time is called the mean free path. Let L be the mean free path of the electron. Then we get L is equal to drift velocity Vd into relaxation time tau. Hence, we get Vd is equal to L by tau. Let this be equation 3. We also get L using the equation of motion S is equal to ut plus half at square in kinematics, where S is the displacement, u is the initial velocity, a is the acceleration, and t is the time. From this equation of motion, we get L is equal to half a into tau square, where a is the acceleration of the electron. Substituting the value of the acceleration from equation 2 and simplifying, we get L is equal to half e into e by m into tau square. Let this be equation 4. Substituting the value of L from equation 4 in equation 3 and simplifying, we get Vd is equal to half e into e by m into tau. Let this be equation 5. From equation 5, it is clear that the drift velocity of the free electrons is proportional to the electric field strength E and the relaxation time tau. Equation 5 can be further simplified to get Vd is equal to k into E, where k is a constant equal to E tau by 2m. Let this be equation 6. The constant k depends on the material of the conductor and its temperature. Let us now find the relation between drift velocity and current density. We know that the magnitude of the current density, denoted by J, is defined as current per unit area considered normal to the current in a conductor. Consider a cylindrical conductor whose cross-sectional area is A. Let the conductor be connected to an electric source. Let E be the electric field due to the source. If Vd is the drift velocity of the conduction electrons in the conductor, then the net distance travelled by the free electrons in the conductor during the time interval delta t is equal to Vd delta t. The volume of the portion of the conductor through which the free electrons travel during time delta t is equal to A Vd delta t. Let n be the number of free electrons per unit volume of the conductor. Then the number of free electrons within the volume considered is equal to n A Vd delta t. All these free electrons cross the area in time delta t. Hence, the charge crossing the area A in time delta t is given by delta Q is equal to NA Vd delta TE. Let this be equation 7. From equation 7, we get current through the conductor I is equal to delta Q by delta T, which is equal to NA VDE. Hence, the magnitude of the current density, J, which is equal to I by A, can now be written as equal to NVDE. Let this be equation 8. Substituting the value of Vd from equation 5 in equation 8 and simplifying, we get the magnitude of current density, J is equal to Ne square tau by 2m into E. The magnitude of current density, J, is also written as equal to sigma into E, where sigma is a constant called electrical conductivity of the conductor, which depends on the nature of the material of the conductor and its temperature. Thus, sigma is equal to Ne square tau by 2m. Let this be equation 9. The reciprocal of conductivity is called the resistivity of the conductor. It is denoted by the Greek alphabet ρ. From equation 9, resistivity ρ is equal to 2m by Ne square tau. Let this be equation 10. For a given material, N remains constant. The mass m and charge E of an electron are also constants. Hence, from the equation 10, it is clear that when the value of tau decreases, ρ increases. This implies that as the relaxation time decreases, number of collisions of free electrons increases. The collision of the free electrons with the atoms of the conductor restricts their flow, and this causes resistivity of the conductor. Similar to resistivity, another important property of conductors is mobility. Mobility is denoted by mu and is defined as the magnitude of drift velocity per unit electric field. Thus, mu is equal to Vd by E. Substituting the value of Vd from equation 5 and simplifying, we get mu is equal to E tau by m. Its unit in SI system is meter square per volt second. A potentiometer is a device used to compare the EMF of any two cells, to measure the internal resistance of a cell and also to measure the potential difference across a resistor in a circuit. We generally use a voltmeter to measure the potential difference across a resistor in a circuit. When the voltmeter is connected across a resistor in a circuit, it draws a part of the current in the circuit, altering the overall potential difference that is to be measured across the given resistor. This alteration leads to an error in the measured value of the potential difference across the given resistor. Thus, the voltmeter is not an ideal device to measure potential difference. An ideal voltmeter should have an infinite resistance. As it is not practically possible to have an ideal voltmeter, we prefer to use another device called the stretched wire potentiometer 2 voltmeter, which measures the potential difference across a resistor without drawing any current from the given circuit. We refer to the stretched wire potentiometer as a potentiometer in our context. To understand the principle of a potentiometer, we take a simple circuit, where two cells with EMF, E1 and E2 are connected in a loop such that their positive terminals are joined and negative terminals are joined by connecting wires. A galvanometer G is connected in series in the circuit as shown. If the value of E1 is greater than that of E2, the net EMF is E1 minus E2, and hence the current in the loop is in the direction of the current due to E1. This can be observed by the deflection of the galvanometer needle in a direction. In case the value of E1 is less than that of E2, the net EMF is E2 minus E1, and hence the current in the circuit is in the direction of the current due to E2. Now, the deflection of the galvanometer needle is opposite to that in the earlier case. In case the value of E1 is equal to that of E2, then the net EMF is 0, and hence the current in the circuit is 0. This can be confirmed by the zero deflection of the galvanometer needle. In this situation, the potential at the negative terminals of both cells is equal. Also, the potential at the positive terminals of both cells is equal. Hence, the current in the circuit is 0 and the circuit is called a balanced circuit. Now let us learn about the potentiometer. A potentiometer consists of a long wire of about 10 meters in length, with a uniform cross-sectional area fixed to a wooden board. This is usually done with separate pieces of wire of 1 meter each, fixed parallel to each other to the board, with endpoints connected by copper strips so that the combination acts as a single stretched wire. The endpoints of the wire, say A and B, are connected to a primary circuit consisting of a battery, B, a plug key, K, and a rheostat, RH. Here is the circuit diagram of the circuit we have just described. The end A of the potentiometer wire is connected to the positive terminal of the battery. The end B is connected to the rheostat. When the key is pressed, let I be the constant current in the potentiometer wire along A to B. Thus, the potential gradually decreases from A to B. Let V0 be the potential drop across AB set up by the circuit. According to Ohm's law, the potential drop V0 is equal to I into R, where R is the resistance of the wire. We know that the resistance of the wire R is equal to rho L by A, where rho is the resistivity of the wire, L is the length of the wire, and A is the cross-section of the wire. Thus, the potential drop V0 is equal to I into rho L by A. Here, I is constant as already discussed. The resistivity of the material of the wire rho is constant. As the wire is of uniform thickness, the area of cross-section of the wire A is constant. Hence, the potential drop across any segment of the wire is proportional to the length of the segment. Thus, the ratio V0 to L is constant and is referred to as potential drop per unit length, phi, of the potentiometer, and is measured in volt per meter. Hence, we have V0 is equal to phi L. Let this be equation 1. If we need to measure the potential difference across a resistance in a circuit, we connect endpoints P and Q of the resistance to the primary circuit. Point P of the resistor is connected to point A of the primary circuit. As the connecting wire does not have any resistance, the potential at point P is the same as that at point A. Point Q of the resistor is connected to the potentiometer wire through a galvanometer G and jockey J. Thus, points Q of the resistor and J on the potentiometer wire are at a lower potential compared to the potential at point P or A. If there is a potential difference between points Q and J, there will be a current passing through the galvanometer. Contact is made on the potentiometer wire using the jockey, which is pressed at various points on the potentiometer wire. In this process of making contact at various points on the wire, we come across a point S on it, such that the potential at that point is the same as the potential at point Q. Hence, the circuit comprising points A, S, Q, and P is in a balanced state and the current in the galvanometer is 0. This circuit is also referred to as a secondary circuit. If L is the length of the potentiometer wire between points A and S, and V is the potential drop across the resistor, then the potential drop across AS is also V. The length L is referred to as the balancing length of the potentiometer wire. The ratio V to L is phi, and hence V is equal to phi L. Let this be equation 2. Dividing equation 2 by equation 1 and simplifying, we get V is equal to V naught into L by L. Let this be equation 3. To find the value of V, we need to know the value of V naught. To find the value of V naught, the resistor in the secondary circuit can be replaced by a cell whose EMF E naught is known. Then, contact is made using the jockey at different points on potentiometer wire till a balancing length L naught is obtained. Note that there is no current passing through the cell when the circuit is balanced. Hence, the EMF of the cell is equal to the potential difference across its terminals. In this case, we get E naught is equal to phi into L naught. Let this be equation 4. Dividing equation 1 by equation 4 and simplifying, we get V naught is equal to E naught into L by L naught. Let this be equation 5. This process of finding V naught is called calibration of the potentiometer. Substituting equation 5 in 3 and simplifying, we get V is equal to E naught into L by L naught. Let this be equation 6. To compare the EMF of two cells with EMF as E1 and E2, they are connected in a secondary circuit separately, one after the other, and the corresponding balancing length of the potentiometer wire for each cell is found. Let L1 be the balancing length for the cell of EMF E1, and L2 be the balancing length for the cell of EMF E2. Then, we get E1 is equal to phi L1 and E2 is equal to phi L2. Thus, the ratio E1 to E2 is equal to the ratio L1 to L2. Let this be equation 7. This equation shows the comparison of the EMF of the two given cells. If both cells are to be connected at the same time, we use a two-way key in the secondary circuit for convenience as shown. If key K1 is pressed, the cell with EMF E1 is connected in the secondary circuit and the balancing length L1 is obtained. If key K2 is pressed, the cell with EMF E2 is connected in the secondary circuit and the balancing length L2 is obtained. Now, let us learn to find the internal resistance of a given cell using a potentiometer. The arrangement to measure the internal resistance of a cell using a potentiometer is shown. In this case, a cell of EMF E and internal resistance R is connected across points P and Q in the secondary circuit. An external known resistance R through a resistance box is connected to the cell via a key K' across points P and Q. Here is the circuit diagram for the arrangement. Initially, the key K' is open. This implies that the resistance R is not included in the secondary circuit. This implies that the potential difference across the cell in the secondary circuit is equal to its EMF. Now, the jockey is pressed at various points on the potentiometer wire to find the balancing length. If L is the balancing length obtained when K' is open, we get E is equal to phi into L. Let this be equation 8. When K' is pressed, the resistance R is included in the secondary circuit. The current through the cell I is equal to E by R plus R. Let this be equation 9. Then the potential difference across points P and Q, which is the terminal voltage of the cell, VPQ, is Vp minus Vq is equal to I into R. This is in keeping with Ohm's law. Let this be equation 10. Substituting the expression for I from equation 9 in equation 10 and simplifying, we get VPQ is equal to E by R plus R into R. Let this be equation 11. In this situation, the current from the cell in the secondary circuit does not pass through the primary circuit, as points A and P are at the same potential. Contact is made on the potentiometer wire using the jockey, which is pressed at various points on the wire till we get a balancing length L', where the potential drop across the length of the wire is equal to the terminal voltage of the cell. Thus, we have VPQ is equal to phi into L'. Let this be equation 12. From equations 11 and 12, we get E by R plus R into R is equal to phi L'. Let this be equation 13. Dividing equation 8 by equation 13 and simplifying, we get the internal resistance of the cell, R is equal to R into L minus L' by L'.